Hi, everybody. You got to see some behind the scenes video recording programs there. Anyway, hello. So this video is a pretty unconventional thing for any class that you ever take. But what I'm going to do is I'm literally going to walk through the more or less the entirety of Project 2a in real time as I solve it from scratch. Now, the reason I'm doing this is because this project, I'd say, is probably the hardest in the class, 2a and 2b. And so what I'm hoping is that by watching my thought process in 2a, you'll be really prepared to do 2b really and truly on your own. Okay, so I hope you really enjoy this. You don't have to watch this video, by the way. It's pretty long. There's a bunch of slides, and I'm just putting it out there for those of you who are coming with a little less background, who would like to see, really, from start to finish, how I would approach something, and hopefully you can learn something from it. Okay. Now, just remember that once you get to 2b, you're all on your own. Yeah, before we get started, I want to mention a couple things. Well, first of all, before you start this project, you really need to understand KdTrees. So you should watch lecture 19 and make sure that you understand what's happening in the KdTree insertion and nearest demos, and do the check-in exercises for that lecture. It's a very bad use of your time to try and start working on the project until you understand what you're going to be implementing. The second thing I'd like to mention is that, well, the video you're about to watch, I actually recorded it in a previous semester some time ago. So some of the details will be slightly different, like the numbering of the projects, and I guess the audio quality is kind of terrible, but I still think it's worthwhile. And so I hope you enjoy this, and let us know what you think on the weekly surveys. So without further ado, I'm going to kick this over to slightly younger me, and here are some steps you can take to solve the project. So the first thing I would recommend that you do, and this is again assuming you've already looked at the spec and have some sense of what you're doing, you should write the naive point set class first, and then verify that it works by using the small example given in the spec. And this class is so simple, you shouldn't need to do any kind of exhaustive testing, and I have recorded me solving this problem. So I blurred stuff out, so you can't just copy and paste what's on the screen. Mostly, some of it shows, but once you get to the later parts, I blur out my code. So you can use that. Now, this is actually done in real time. I did it cold. I hadn't done this part of the project yet, so I have my whole thought process, and you may find it useful to watch how that goes. So that's naive point set. That's the first point set you build. Secondly, I'd recommend that you write the constructor for the KdTree class, and that you verify that it probably works by inserting all of the points from the lecture example. So that is, in lecture, I give an example of KdTree insertion, and I end up with this KdTree. So you can verify that you actually get this. Oh no, baby's grumpy. Anyway, you can verify using the Java visualizer that your insertion was correct. Now for this part, I recommend that you use the BST map as a template. So in Lab 7, you built a binary search tree. This will feel a little bit similar. You'll need as you go along to decide what variables to include in your node class. And I'll say there's lots of stuff you could do, but at the very least, you're going to need a point, you're going to need a left child, a right child, and I would say in general, keep things as simple as possible. You can always add more stuff if you need it later. Now you do not need to worry about balancing your KdTree. The worst case is spindly, but the autograder will not give you such inputs. One thing you can do is shuffle the points before you start, but it's not required. So again, I have a video of myself solving this problem. You can watch as I write the KdTree constructor, and again, I blur out the code to avoid spoiling everything, but my thought process is there, and there's still some code that shows that might be useful. I also have a video where I use the debugger to verify that my KdTree constructor works. And so you might find this helpful, so you can see how I make sure my constructor works. Okay. So again, you don't have to watch those videos, but you might find them useful. So once you have the constructor for KdTree working and you think it works, or once you've built it and you think it works, you should then move on to writing the randomized test that compares your KdTree nearest method to naive point set nearest method. So we give example, or we explain how this test should work, and basically you should generate a few thousand random points that are going to be in your trees, and then a few hundred random points to be used as arguments to nearest. We recommend that when you do this, you actually write the test before you write nearest. So nearest should just return null for KdTree. You should run it, and it should fail, and your goal is now to get it to pass. Now, alternately, if you don't want to write a randomized test first, because it seems like a little bit of a mental block, you can start with a simpler single test. So for example, you could start by inserting these 6 points and then making this call to nearest. Oh, sorry, wrong demo. You can start by inserting these 6 points and then calling nearest on 0, 7 and verify that you get 1, 5 back. Though I'd say that the randomized test also isn't so hard to write. Now I again have a video where I will go through this process, including, and in this case I'm not going to blur the randomized tests. I don't think it's processed yet, but this will actually show my code for the randomized test that you can use, and you're welcome to use the ideas that I put out there in this video. Just don't literally just type my code, right? That's lame. If you do use my video as a source, make sure to cite it if it ends up being pretty similar. So what else do I want to say about this? Oh, in this video, I should note that I didn't do it in this order. I actually wrote a simple test, then I wrote nearest, and then I wrote a randomized test. But even though that's what I did, in retrospect, I would have preferred to have written a randomized test first. So that's what I'm recommending you do, but you could do whatever you'd like. All right, fourth. So next up, you need to actually implement nearest. So I'd say rather than try and go straight to the fast version, you should write an inefficient version first. This version should always search the left subtree, then the right, and should not do any pruning at all. It should, and then you should test it using your test from number 3, and it should pass. And some example pseudocode, which is also given in the lecture slides. Let's see, where are we at? In the lecture slides, this is an inefficient version of nearest. So I'm not going to talk through it. Well, actually I will. Why not? Okay, so this nearest method basically does the following. So given a current best, a node that you're searching, and a goal, if n is null, you just return the best because you're not going to do better. It's a null tree. If the distance to the goal given by this node is less than the distance from best to goal, then we should set best equal to n. Now this is just pseudocode, right? It depends on your node method. Like you would have to have a distance method for your node class for this to make sense. So you might not have that, and that's fine. You just need code that does the same basic idea. And then once you've updated best, if indeed n is better than best, then we need to say, okay, well, let's compare this best that we currently have against the left child. So this function will give it our current best, our left child to explore, and the goal point, same goal as before, and we'll set best equal to the result. Then on the right side, we'll say the best item, well, that's going to be same deal. We're going to search the right child and replace the old best with the new best if indeed we find something better. And then finally, we'll return best. So the best of everything I've searched. Now this should be a really short implementation. I'd say less than 12 lines of code. I think mine was like 8, something like that. Now I'll note that this is actually going to be extremely slow. It's actually going to be slower than the naive point set. So in other words, we built this KD tree that's a much more complicated data structure than the naive point set, but here it's actually super slow because this nearest method, it has to traverse a big tree. It's a lot of overhead, so it'll be bad. Okay. Now the reason I suggest this though is that way you at least have something that works, and then you can make it better. So step 5 is to add another test that compares the timing of naive point set to the KD tree. I would recommend, since the spec gives the example, using something like 100,000 points and 10,000 query points. That is, we're going to call nearest 10,000 times. Although you might increase this points value in order to get a stronger distinction between the two, that is naive point set and KD tree. I don't know, up to you. So it's okay to just print the 2 different times, or you could do something like an actual test that asserts true that the KD time divided by the naive time is less than 0.1 or whatever. But I just printed them out and checked to see what happened. Now I should note that at this point, your KD tree will be much slower than naive point set if you're following my recommended progress steps. Now I don't have a video edited together for this yet. I'll do it as soon as I can, but it'll be in this slide eventually. Now as before, don't just copy down my timing test. You should cite your sources. Now, the 6th thing I recommend you do is you should modify your nearest method so that it considers the good side first, then the bad side. So in other words, instead of always doing left then right, let's do good then bad. And don't worry about the pruning step yet. So if we look at the pseudocode from lecture, which I'm not going to go through here yet. No, you know what? I'm going to do it. I'm going to do it. Why not, right? So this nearest method is quite like before. If it is null, we just return best. If the thing we're looking at is better than best, we update best. And then, here's the interesting part. If the goal is less than n, according to n's comparator, so if we're splitting the space in half by x coordinate, if the goal is on the left side, then we'll say the good side is the left child and the bad side is the right child. Otherwise, it's the other way around. The good side is the right child and the bad side is the left child. Okay, so we'll set those up. And then we'll say best equals the nearest, considering the good side. And then for this part of the project, what I'm recommending, oops, where'd I go? What I'm recommending is, I lost my slides. Oh, here we go. So what I'm recommending is ignore, for now, this pruning rule. Just do this, then that. So search the good side, then the bad side, always. Okay? And when you do this, if you do it right, your code will still pass the tests, and it will be equally slow. In other words, it'll seem to have no effect. So ideally, once you've done this, your code should be just as slow and should be correct. And then lastly, the final step of the project is after you have this code working, but without this if statement, you should try and add this if statement. Now it's just one if statement, seemingly, but it could be a little tricky. And that's why I really recommend that you do this incremental approach, where you first start with an inefficient solution that looks through the tree left then right, followed by good then bad, and now finally this third version, your job is to add the pruning rule. Now there's one really important warning I should mention, which is that the point class, it computes the squared distance. That is, it's the distance between, the distance according to the point class between 0,7 and 2,3 is going to be 20, not square root 20. And that's just because, for efficiency reasons, we decided to omit the square root, so everything's a little faster. However, the one tricky part here is that if you are trying to use the, so you may recall there are two pruning rules. There's the purple version, which is pickier, but tricky, which is better but harder to implement. And there's the green line pruning rule, which is easier to implement but not quite as good. So if you try to use this green rule right here, the simpler one, which is what you should be doing, you cannot just compare goal.y minus d.y with the distance to best. Okay? The reason is that we're using the squared distance. So you'll need to use the squared difference in y's, or what you can also do, and maybe this makes no sense at this point, but what you can also do is actually create this point as an object, and then use the point.distance method in order to compute the distance from the best hypothetical point and the current best. Okay? Now, really, if you're, maybe not at all at this point in the project yet, come back to this video as you get closer, and I hope that will make more sense. Now, once you're done with this, you should run your tests again, and they should pass, and your KdTree should be much faster, ideally somewhere at least 30 times faster. So I hope this set of walkthroughs and these pieces of pseudocode make your life better. Yeah, good luck with the project, and I hope we don't run into spring break too hard. And if, yeah, well, I'll keep my eye on things, and hopefully things will be good. All right, have a good day. Good luck with the project. See you soon.